Did you all revise? And if you have revised, we will continue from what we did yesterday, including method of calculation of capacitance. So let me ask some of you. Do you recall what is the method of calculation of capacitance? All of you recall that part? What is the method to calculate capacitance for any kind of two conductors? Chandra Kaushik, what is the method of calculation of capacitance? Can you tell me in simple 3-4 steps? What is the method of calculation of capacitance? Akshat? Akshat, are you there? Okay, no answer. Kevin?
Yes, sir.
What is the method of calculation of capacitance? Do you recall?
Sir, the formula.
No, what is the method, steps involved? And in fact, we have yesterday, but separately mentioned steps involved in calculation. Any two conductors are given. See, in case of parallel, we found yesterday capacitance for two parallel plates. We also found capacitance for two concentric spherical shell. We also found capacitance for a single sphere. Three things we found capacitance for. And you are still not sure what is the method for finding capacitance, which is disappointing. Disha, what is the method of calculation of capacitance?
So first we give them equal and opposite charges to the two conductors.
Yes.
And then we find the Q by V ratio, like we find the potential difference between the conductors.
But directly, yes. So either we find potential, or sometimes if we cannot directly find, first we need to find field, and then we find the potential difference. To find potential difference, sometimes we first so you give a charge plus Q minus Q. Either directly find potential if potential formula is available. If not, find the field, and we calculate potential difference using line integral of field from one conductor to the other, and take the ratio, we find capacitance. Okay, and so we will do for one more case today, slightly more complex. And some of you who are asking about charging of capacitor, what has happens when we connect a capacitor to a battery? Let's understand that again based on some other way. I thought one more way you can try and explain what is the process of charging a capacitor. So okay, so on the top you see a capacitor is connected to a battery. We know this also is, everything is a conductor. The moment we connect one conductor to other, which direction the positive charge flow? We should always think in terms of positive charge. In terms of potential, the positive charge flow from where to where? From higher potential to lower, or lower to higher? It flows from higher potential to lower potential. So let's take this plate here, the positive potential plate of the battery, and this plate are connected. Among the two, this is initially at zero potential, this is at positive potential. So how would the charge flow as far as this plate and this plate of capacitor is concerned? The charge will flow from this direction to this. So direction of flow will be from battery to the plate. What will the charge flow in terms of negative plate of the battery and this capacitor, this plate of the capacitor? Which will have higher potential? Between the both are conductors. This is a conductor, this is a conductor. Which has higher potential? This has no charge initially. This has negative charge. So which one will have purpose? This one, if no charge means it will have zero potential. If I don't know the magnitude, if it has negative charge, I can take it as a negative potential. So which is a higher potential?
The capacitor plate.
Capacitor plate has higher potential. So here what will happen, the positive charge will flow in the downward direction. It will flow from the capacitor to the battery. So that's what you should keep in mind. So positive charge flows from higher potential to lower potential. Consider two parts, as I mentioned here, for the direction of charge flow or current flow. How would the charge flow? I hope all are clear. This is what indicates. In left part, it flows from positive plate of the battery to the plate of the capacitor. Here it will flow from, charge will flow out from the capacitor plate. If the positive charge is moved out from the plate, it will acquire negative charge. This positive charge is flowing into the plate, it acquires a positive charge. Effectively, we can think of what is the role battery is playing here, is shifting the charge from negative plate to the higher plate. is something like this. If two water tanks are there, water is at the same level. You connect a pump, start pumping water from one tank to the other. What will happen for one tank? It is pumping from the level keep down, other tank the level will keep going up, and up to the capacity of the pump, the level difference will happen. So something like this, the way the pump transfers water from one tank to other, and so that one tank the lower level keeps coming down and other keeps going up. Something similar. What does battery do? It transfers charge from one plate to the other against the it transfer against the gravitational force. Here it transfer against the electrostatic force. It increases the potential. It supplies the energy. It continues till the potentials become equal and charge becomes plus q minus q, such that we know one formula we should very often, we'll use very often. The formula is q is equal to c is equal to q by p. So what is v equal to? What is the charge finally it will have? So the charge transfer will continue such that they acquire a charge of plus q minus q, such that the potential difference becomes equal to potential of the battery. Okay, q is equal to c. That charge will take. Now, this is the case given here. How many shells are there? 3 shells, 3 conductors. Do 3 shells form a capacitor? No. So our discussion so far had been we need 2 conductors to form a capacitor. Even one conductor also I can treat as a capacitor by treating the earth as a second conductor. But if there are 3 shells do not form a capacitor. But if I connect one shell to the other, now are there 2 conductors or 3 conductors? Moment I connect A and C with a conducting wire, A, C with wire put together, it becomes like a one conductor. There are only 2 conductors now. Can we calculate capacitance of this arrangement? What is the capacitance of this arrangement? Can you try and calculate capacitance for this arrangement? Please do that. What is the method of finding capacitance? Identify 2 conductors. One give a charge plus Q, other give a charge of minus Q. Calculate the potential difference. Q by potential difference is equal to capacitance. Can we do this calculation? Find capacitance of this arrangement.
Sir, what are the charges on the spheres? Nothing.
To find capacitance, do we need charges? Does it depend on the charge at all, first of all? Capacitance is equal.
Not necessary.
Yeah, not necessary. So again, to remind everybody, capacitance is independent of charge. It only depends on geometry. Geometry means the way it is arranged, conductors. So first we notice, are there 2 conductors? There are 2. AC put together is one conductor, B is another conductor. So I have to place one charge on B, other on AC together. I place it anywhere, the charge will get distributed between A and C. So method is I'll find the charge distribution, I'll find the potential difference. And potential difference, Q divided by potential difference is my capacitance. So first hint, that's what I said. Charge plus Q we place on B and minus Q on A and C together. When we place, the charge will arrange itself. Some part will go to C, some part will go to E. How do you find that charge flow? With the charge distribution. We need to find a small q first. You find a small q. After finding a small q, what is the potential difference? Potential difference I can take between B and A, or I can take between B and C. Both will come same. Asha, you have an answer? Or you have some query? Doubt. Tell me what doubt you have.
So why can't minus q go on B?
Still the answer will come same. It doesn't matter. Yeah. There we are calculating potential difference is potential of the positive plate minus the potential of the negative plate. So it doesn't matter which is given positive, which is given negative. How do you find charge distribution? We find charge distribution, those who need little hint. First, if we give charge plus Q, some charge will go on C, some will remain, and some part will go to A. So what we are assumed here, the charge on A is small q. Since the total charge on A and C as a system has to be equal to minus Q, the charge on the C shell is equal to minus of Q plus C. So that both put together is equal to minus Q. How do you find value of small q? Find the charge distribution between A and C. How do you find charge distribution? By equating the potential of C to A. What is potential of C? Net charge enclosed. Potential at C is equal to 0. When net charge enclosed is 0. Potential at A we calculate, equate it to 0. So based on this simplification, we get value of small q equal to minus q by 4. So this will be minus q by 4. And if this is minus q by 4, this will be minus 3q by 4. Total has to be minus q. What is next step then? Then I'll calculate potential difference between A and B, or I can calculate potential difference between B and C. Either way is same. Potential of B minus potential of A, or potential of B minus potential of C. Any of these two, since potential of A and C are equal, any of the two will give you the same result. So potential difference between A and B will come into this value. Once you have potential difference, capacitance is equal to what? Capacitance is equal to Q by B, 8R by K, substitute value of K, 1 by 4 pi epsilon naught, thus value of capacitance. So though most of you have not done it, but if I give another question with 3 concentric shells, 2 of them connected by a wire, how many of you can do it now? Please raise your hand. Those who are confident, they can do it now. Have they understood what we have done here? We have not done anything new, but can we do it now? Have you followed all the steps? Good. So several of you feel you can do it. Pranav, are you sure? Pranav Soma.
Yes, sir.
You can do it now. You followed the steps. Have you done anything new? No. See that each step is understood. So any similar question, this is not one of the easier question, but if you can do for this question, I think then you're good in method of calculation of capacitance. Okay. Good. So several of you are okay. So those who are not, again, I think need to practice a little bit more after the session is over. Again, go through, see what you have done, see that every part is understood. And if not understood, again, you have time in the evening. Come and we'll discuss it again. Okay, how about cylindrical capacitor? Can we calculate capacitance of what it is like? There's an inner cylinder, there's a concentric outer cylinder. So 2 conductors are in form of 2 thin cylinders. And what we need to assume here, the length of the cylinder is much longer compared to lateral dimension. So length is large, which length is large means length is much greater than the radius of the shells, cylindrical shell. How do you find capacitance of the system? What is the method of finding capacitance? We don't have formula for potential here. So what we need to do, we need to give them charge and they calculate potential difference between positive conductor and negative conductor. What do we need for calculation of potential? For calculation of potential, we need to know the field. Do we know the field in the region between the two cylindrical shells? Do we know the field between 2 cylindrical shells? Information given is radius of the inner shell is given as capital R1. Radius of outer shell is given as capital R2. I need the value of field for value of R which is greater than R1 but less than R2. What is the value of field for a small r? Which is for a point lying between the 2 shells. What is the field? And what is the nature of field if the cylinder is large? One way, again I give a hint. Actually, if the cylinder is large, can I treat this inner cylinder as a charge line charge, long line charge, lambda? Can I treat that inner cylinder as equivalent to line charge? The way for sphere, we treat as a point charge if we are calculating field outside. Similar way, if you look at the Gaussian surface, if the charge is cylindrical in shape, for a cylinder outside, it doesn't matter what the side of inner cylinder is, I can treat as a line charge. Are you following how it can be treated as line charge? If it is a line charge, what is charge per unit length? If total charge given is Q, if the length of the cylinder is L, charge per unit length on the cylinder is Q by L. Have you understood this point here? Advay, have you followed what I said? Chandra Kaushik? Harsha? Hemant? Ritika? Anish? 5 names, no response, no yes, no. What's wrong?
Repeat it once.
Some of you are very slow. They don't respond. Okay. Samhita, have you followed?
Sir?
Yes. Are you following what you are doing now? Have you followed this point or not?
No, sir, this is bad.
Hmm?
Can you repeat this point once? My power wasn't exactly the same.
Okay. Even now also, okay. What is said, just look at the question. What are we trying to do? See, we are trying to find the capacitor of two cylindrical shells. You understand what is cylindrical shell? The two concentric cylindrical shell, long cylindrical shell. So their length is much more. So this something is this one can be like a thin, like a pen, like a thing, and there's another cylinder of a radius slightly greater. So we have two long cylindrical shells. We want to find out what is the capacitance. So to find capacitance, what we have done here, we have given a charge plus Q to the inner shell. This is not a spherical shell, cylindrical shell, minus Q to the outer shell. To find potential difference between positive conductor and a negative conductor, I need the field in the region between the two shells. What I'm saying now, this field between the two regions is equivalent to field created by a line charge. Have you understood why it can be treated as a line charge?
Sir, because length dimension is
Length dimension is
than-
large, and as we can in case of sphere also, because of spherical symmetry, it doesn't matter what the size of the sphere as long as inside the Gaussian sphere shell what we take. Okay. So similar way, if I take a Gaussian surface in form of a cylinder, which basically encloses this inner cylindrical shell, it doesn't matter what the radius of shell is, charge impulse will remain the same. Even if it was a line charge also, with equivalent line charge per unit length, it remains the same. So I can treat a cylindrical shell as equivalent to cylinder of negligible radius, which is a line charge. And what will the line charge? What will in case of line charge, my formula is field due to line charge is lambda by 2 pi epsilon naught r. The lambda is charge per unit length. Here total charge is Q, length is L, L is the length of the cylindrical shell. So lambda is Q by L. Now I can use the field, I can calculate. If you look from the top, this is the inner shell, this is how the field lines will look like. This is how the field lines will be. Field lines will emanate or start from the inner shell and go up to the outer shell. Is there any field line outside? Outside there will not be any field. Why there is no field outside the outer shell?
charge enclosed.
Charge enclosed will come to 0. Okay, so either I can apply the Gauss law and calculate, or I can directly apply the formula. Field is equal to lambda by 2 pi epsilon naught r. If this field is like this, I need to calculate potential difference between these 2 points. I need to calculate potential difference between positive conductor and the negative conductor. So initial point is at a distance of r1, and final point is a distance. But see, I have to calculate potential difference between these two. So initial point is this one. So V plus minus V minus. So that's what you need to calculate. So I'll start, V is what? E dot dr from the starting point R2 to final point R1. I am calculating potential difference between negative plate and the final positive plate. The positive plate is final one, negative plate is the initial one. Thus we calculate difference. Yes.
So isn't it positive minus negative, sir?
Yes, positive minus negative. So which is the final thing comes?
Positive.
Positive.
Okay.
So which is the final one here? So what should I go on this side? Now final value? R1.
R1,
Positive
sir.
plate. Yes. Any doubt?
No doubts.
Yes. So starting from so R2 to R1, if I integrate, it's a simple integration. It's a integration of 1 by R, which is logarithm of R, and we substitute the limit, and this is what the expression we get here. And this particular question, actually not many applications come. I look at one or two simple application because formula normally doesn't come in the examination. It may come in the internal examination. So I hope you understood this V. From this, can we find out capacitance? Capacitance is Q by V. So this is the term of capacitance. What is the important thing we notice here? Of course, it is proportional to length. If we double the length, what will happen? The capacitance will become double. It is in proportion to length. Other thing what we notice in terms of radius, it depends on the ratio of the radius. So if I have one capacitor which has outer radius 2 centimeter, inner radius 1 centimeter. If I have another capacitor which is of the same length, outer radius 10 centimeter, inner radius 5 centimeter. Since the ratio of radiuses are same, both will have same capacitance if length is same. That's what this means. So in terms of radiuses, what does it depend on? It depends on log of the outer radius minus the log of outer radius divided by the inner radius. That's what the formula is. Do we need to remember the formula? I don't think so. This formula not necessary. Or if you those who are good, they will easily remember this part. It should be E dr, limit being from outer radius to inner radius. You can derive it in less than half a minute, and you can do that. Okay, so that is cylindrical capacitor. Now today we'll also look at what is something which is important and not very complicated. Most of you must have done equivalent resistance in your school also. You recall doing something parallel and series? All of you must have done. And you may recall something about parallel and series combination of resistance. Similar way we have combination of capacitor. So if you have number of capacitor, they can be connected to circuit in variety of arrangements. What you are looking at, if you have a number of capacitors connected in a circuit to battery or whatever, how would they behave? So we are looking at a combination of capacitors. So two or more capacitors. So let's see this one. Let's go through the combination. It is something similar to what you have done in case of resistance connected in series and connected in parallel. All of you may recall when you connect resistance R1 and R2 in series, equivalent resistance is R1 plus R2. When you connect them in parallel, 1 by inverse of equivalent resistance equal to 1 by R1 plus 1 by R2. So that you might recall from your school days. Let's proceed further here. Two or more capacitors can be connected to the battery at 2 points which are potential difference equal to EMF or voltage of the battery. So not necessarily across the terminals of the battery, not necessarily only one capacitor. I can connect multiple capacitors. Okay, so that's the number combination we connect. But whenever we connect a battery, whatever combination we connect to battery of potential V, any combination will supply some charge. Some charge will flow through the battery, as we've seen earlier. How much charge it has transferred? It has charge transferred Q from a terminal on the negative side. It has transferred charge Q to the positive side. So each terminal battery, either I can say supplies a charge of plus Q minus Q, or I can say the battery what has done, it has transferred charge Q from negative side to the positive side to the system of capacitor. So the capacitance of capacitor, which is connected a combination, depends on charge Q transferred. If for one combination charge transferred is more and other system of capacitor charge transferred is less, what does it convey? C is equal to Q by V. If battery remains same, the capacitance of the system of capacitors depend on the charge which is transferred. If charge transfer becomes double, it means that system has twice the capacitance of other one. So each terminal battery supplies charge plus Q minus Q, or it transfers the charge Q from the negative terminal towards the positive terminal side. The equivalent capacitance of the system, though there are many of them are there, I can treat them as one capacitor. What is the equivalent capacitance of the whole system? Is equal to charge transferred by B. I hope this logic is simple and clear. The equivalent capacitance of system of capacitors connected to 2 point is equal to charge transfer by B. If whole system is replaced with single capacitors of capacitance equal to C, it will behave in the same fashion as the combination of capacitor. So what is the equivalent thing? If charge flow, if connected to battery, if two systems have same charge flow, it means two systems have equivalent capacitance. One of the system can have more than one capacitor, other system has only one capacitor. Then one capacitor is equivalent of the other system of capacitors. So if above system is replaced by single capacitor of this capacitor, same charge, hence it could be treated as an equivalent capacitor for a combination of capacitors. Let's do that one in some cases. Here what we have, this is a simple thing, but we'll do slowly and see that every part is understood. These three capacitors are connected in series, and where the battery is connected at these 2 points. These are terminals of battery, X and Y. So in X, Y, what is potential difference between X and Y? Potential difference between X and Y is same as the potential of battery B. This is how they are connected. Potential B is applied across three capacitors. Each capacitor has two plates. The plates are numbered as A1, A2 for first capacitor C1. Second, they are not identical capacitors. Second one is C2. Plates are A3 and A4. They are numbered so that we identify each plate separately. What will happen when you connect? So as we say, each terminal battery will supply charge plus Q to A1 and minus Q to A6. So what the charge transfer takes place from here? Plus Q will go to this side, and this side it can only reach, the charge can only reach A1. Can it go beyond A1? No, this is separation, so it can reach A1. So if this supplies charge Q here, this side, this charge Q reaches A1 and minus Q reaches charge A6. You could have also thought of it shifts charge Q from A6 to A1. Both are same. So what is the charge here? Oh, okay. When I transfer the charge, this has charge plus Q, this charge minus Q. Any of the plates, do they have any charge? They don't have any charge. So if I take all 6 plates together, what is the net charge on all 6 plates together? Net charge on all 6 plates put together is 0. Hence, the outer surface here will have 0 charge. Outermost surfaces will have 0 charge. So where would the charge Q will go? What is the, I hope you understand. Inner surface of A1 will have charge plus Q, and inner surface of A6 will have charge minus Q. So whatever charge I have given to A1, it is not on the outer surface, it is on the inner surface. Whatever charge is there on A6, there is also in the inner surface. That's how the charges are when the plates are connected, when the charge transfer takes place. But that's where the story will not end. Something more has to happen. Why something more has to happen? If this face has a charge plus Q, opposite charge has to have minus Q charge. Then only if you take the Gaussian surface, net charge impulse has to be 0. Okay. So moment you have this charge Q, left surface of A2, if this has charge Q here, the left surface of A2 has to charge minus Q, and this charge is minus Q, this charge surface has to have plus Q charge. That's the next point. Is that easy enough? So left surface of A2, I hope this point also is clear. I've written all points in detail. If you're not understood, you can go through that again. So that's the next step. This also we can, this has to happen. But here also still the whole thing is not complete because other plates are left. Let's look at what will happen further after this. It's A2 and A3 form an isolated system. This whole system, initially it has 0 charge. Now they are not connected to anything else other than to themselves. So net charge on the whole system has to remain 0. If this has charge of minus Q, the plate A3 has to have charge plus Q. Similar way, A4 and A5 also form an isolated system. If this has charge plus Q, this has to have charge minus Q. So thus we can continue that one. So the charge on this, and where would the charge go? Again, the charge has to be opposite to each other. So that becomes the charge distribution. What we notice here, when we series, these are connected in series. What is the charge on first capacitor? What is the charge on second capacitor? What is the charge on the third capacitor? All 3 capacitors will have equal charge. That's a property of capacitors connected in series. all capacitors will have the same charge Q, and one of the plate, which plate will have the plate which is on towards the side of positive terminal of the battery will have positive charge, other will have negative. So here this is positive, negative, positive, negative, or the two plates connected, one will have positive, one will have negative charge. So what we have figured out, when we have combination of batteries, a combination of capacitors connected in series, we have figured out what is the charge distribution based on very detailed understanding. I hope all of you have been following so far.
Sir,
Yes.
sir, in the A3 and A4 plates, what about the charge on the inner and outer surfaces, sir?
Even there also, see, actually in this case also, the field in this part will be 0.
Yes, sir.
Okay, so where also all the charge is always on the opposite faces only. So see, whole system, see, this charge where from it has come, this has come from the battery.
Yes, sir.
And this charge also is because of connection battery. But this charge also, first of all, the charges cannot remain in the outer surface, because if I take the whole system together, net charge is 0. Outermost surfaces will have 0 charge. This charge is on the inner surface. Moment this has a plus Q charge, other one has to have minus Q. Moment
Yes,
this
sir.
has a minus Q, this plate has to have plus Q charge. And where the plus Q charge will be on the this facing surfaces.
Sir,
So
what about the outer surface of A2, sir?
what about charge on the outer surfaces of A2? If I
It should have
take this
plus
as a
Q.
system, if I take these two charges as a system, suppose they are separated capacitor, what will happen in this two? What is the net charge on this system? Is 0.
Yes, sir.
Okay, so if this is 0, outermost surfaces have to have 0 charge.
Yes, sir. Yeah.
So nonetheless, okay, don't prove it will come. So basically, other thing what we notice here, charges are equal and opposite. So where the fields are only between the plates. Anywhere else, there's no field. And actually, also connect the capacitor, you find field is only in the region between the plates of the capacitor, none outside. Okay. So what is the important point here? Okay, so three capacitors connected in series and potential difference. Now we come to, okay, the charge is Q, plus Q minus Q, plus Q minus Q, plus Q minus Q. All three capacitors connected in series. Yeah, another important point also, why the charges were equal and opposite on these two plates? Because they were isolated. What does isolated mean? These two plates are connected to each other, nothing else. They are connected only to each other. There's no third connection. There's no other connection to some other conductor. Then only these two plates are isolated, they'll have equal and opposite charge. So that's an important condition for series connection. What important connection for series connection? If two capacitors are connected in series, the plates are directly connected without any branching in between. Then only it is series connection. What is series connection of two capacitors? Two plates are directly connected to each other without any branching in between. The moment there's any branch, something else is connected, that's not a series connection. Then charges are not equal. So that's a series connection. Charges will be equal. Plates are directly connected to each other without any branch in between. Now coming to what the charge will be, let's do that calculation. So basically, see, when you look from this point, as compared to point X and Y, see, many times what we do, either I can take this point as positive potential and this as negative potential. But we are more concerned with potential difference. It is much easier. We take potential of the negative plate to be 0. Potential of positive plate becomes equal to V. What is potential of point Y? And okay, Harsha, what is the potential of point Y? If I assume the potential of negative plate of the battery to be 0, what is potential of this plate? 0. In that case, what is the potential of point Y, Harsha? Potential of point Y if potential of the negative plate of battery is 0. Anish?
Yes, sir.
What will the potential of point Y?
0.
If this point potential is 0, since it is connected by same conducting wire, all points which are connected together have to have same potential. This also will have 0 potential. And if this is 0 potential, since potential difference is V, what has to be the potential of the positive plate? V. If potential of positive plate is V, what is potential of X?
V.
Huh?
V.
V. So between these 2 points, X and Y, potential difference is V. as we come like this, like also. But suppose I go along this path here. I go from X to Y along like this also. Along this path also, potential difference is independent of path. Here also, the potential difference should be equal to what? Same V.
Yeah.
Okay, so that's the point we'll apply now. What point we are going to apply? Potential difference between X and Y, X being Vx minus Vy is equal to V. So if I go along this path also, potential difference is equal to V. How are we going to calculate potential difference is pretty similar, simple. You know, in the household also you have batteries. Sometimes you see this, each battery is 1.5 volts. And how to many times how we connect this battery? We keep this battery like this. We connect like this. We connect them in series. If you connect 3 batteries, what is the potential across the 2 ends of the battery? If 3 batteries of each of 1.5 volts is connected, it becomes 4.5 volts. It becomes sum of the voltage. Something similar happens here. So we'll do that part also. Let's do that part. Potential between X and Y is V. As we move from X to Y, the field exists only between the plates. Hence, the potential, as we move from X to Y, potential will change from here to here only. In between, from here to here, no change in potential. Then there's some change in potential here. And there's some change in potential here. Which is what the potential here? Change in potential between 2 plates of the capacitor is nothing but the potential of the capacitor. In essence, what he is saying, what is V equal to? V is equal to potential of C1 plus C2 plus C3. What is V equal to? Potential of capacitor C1 plus potential of C2 plus potential of C3. Do we know potential of, how do we calculate potential of a capacitor? Potential, how are 3 quantities related? C is equal to Q by V, or potential of a capacitor is Q by C. Potential of capacitor is, if I know the charge, if I know the capacitance, I find the potential, which will be higher. Positive plate will be higher potential. This will be at a lower potential. So that's what you're going to write that equation. What is V1 minus V2? I'm writing what does V1 indicate? Potential of this plate A1. And V2 indicates potential of plate V2. This is nothing but potential of C1. That's what we defined yesterday. This will be equal to charge by capacitance. Only one formula we are using. We are using the formula C is equal to Q by V. So this is V1 by V2, V1 minus V2. Similarly, I can calculate V3 minus V4 will be equal to Q by C2. And third one also calculate V5 minus V6 will be equal to Q by C. What is sum of these 3? If I have equivalent capacitance V is equal to Q by C, or V is equal to Q by C. If I replace whole thing with one equivalent capacitance, that also should draw same charge Q for given potential. And what does C is? C is that equivalent capacitance. So V is equal to Q by C for equivalent capacitance of the system. We equate V is equal to sum of potential drops. So Q by C is equal to Q by C1 plus Q by C2 plus Q by C3, or we get 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. How did we get this equation? 2 steps. We have taken long path, but what are the 2 steps involved? All capacitors will have same charge, and sum of potential across all capacitors will be equivalent to overall potential of the battery. These 2 conditions we apply, we get this result. What is the result we find? Inverse of the equivalent capacitance is equal to sum of inverse of each capacitance. 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Okay, Ashrey?
Sir, I didn't understand why there won't be any field between A2 and A3.
Okay, see, if we have a capacitor, suppose we have a parallel plate. Don't forget about capacitor. If there are 2 parallel plates, we give a charge plus Q minus Q. What is the field in the region outside those 2 plates?
0, right, sir?
0. So these 2 also is like this. Either I can take together, I can take one system, one pair of parallel plates, another pair of parallel plates, third pair of parallel plates.
Okay.
All of them. So basically, the field in this region will come to 0. Charge will be equal and opposite. Okay, so if I look from, as I move from here to here, up to this point, no field. Anyway, it is conductor. Where the field will exist? Only from this point to this point. Will there be any field from this point as we move along this point? Will there be any field along this path here?
No, sir.
No, conductor. Again, field will exist from here to here.
Yes.
Again, from here to here, no field.
No field.
Again in 0. So that's the reason. So basing that, in essence, what we figured out in case of series combination, how do you define series combination? Since you raised the question, How did I define the series combination of capacitor? How did I define? What is the way to define series combination of capacitor? The plates of capacitors connected in series have direct connection. There is no branch in between. Then only the charge on the capacitors connected in series are equal.
There's the
What
same
is
current
series
flows through it.
combination? So basically only one direct connection between the plates, no branch in between. Then I can be sure, yes, these are connected in series. Here also I notice direct connection means C2 and C3 are connected in series. So what is the check to make sure that it's connected in series? Direct connection, no branching in between. If there's a direct connection, both will have same charge because of isolated system. That's the property of series connection. Charge is common. Another thing, last statement, have you understood? Potential gets shared in inverse proportion of capacitance. So total voltage we apply here, yes, potential across C1 plus C2 plus C3 also is V. So whatever quantity V, it is divided into 3 parts. Who gets major share? Q is same. So what is V1 proportional to? V is proportional to 1 by C1. Potential across second capacitance is proportional to 1 by C2. So what we notice here, which proportion is the potential gets shared? Who gets more share? It is an inverse proportion of capacitance. Do we all understand what does inverse proportion mean? If you have two capacitors, the one which has higher capacitance will have lower potential across it. Is the last point clear? Sai Shreya?
Yes, sir.
Yeah. Have you followed? So what is series connection? Simple thing. What are the points you understand in case of series connection? How are the capacitors connected? Plates have direct connection. Charge on all capacitors connected in series are equal. Voltage applied to capacitors connected in series is shared. Which proportion it is shared? Inverse proportion of capacitance. Is that something you need to remember? It doesn't have to remember. Where does it come from? V is equal to Q by C. Since Q is same, V is inversely proportional to C. These are the key points in series combination. All of them are pretty simple ones. I expect all of you to easily remember those points. Not easily, understand those points. Ritika, what did you say about series connection? Grishma? Series connection, what are the points I mentioned?
The potential changes between the plates.
No, I didn't start with that. No, what is series connection? If we have capacitors, we have to connect those capacitors. How are those capacitors connected? The plates of the two capacitors are connected directly without any branching in between. So when you look at the figure, we can understand, is the connection direct between the plates or is there any branch in between? If the connection is direct, it is a series connection. So how do we identify series connection? Plates of the capacitors connected in series are connected directly, no branch in between. If they are connected directly, then only the charges are equal. So charges on capacitors connected directly in series, charges are equal. And potential what we apply to capacitors connected in series are shared in inverse proportion of capacitance. Thus, Gayatri, can you repeat what I said?
Yes, sir.
Yeah, tell me what.
In series, the capacitors are connected in directly.
Yes.
And then all capacitors will have equal charge.
Equal charge.
And potential gets shared in inverse proportion of capacitance.
That's a simple 3 points. And in terms of formula, it is if you remember formula for resistance, it is interchanged. What happened in case of parallel connection resistance, it is happening in series connection. You recall in case of resistance we used to write 1 by R equivalent is equal to 1 by R1 plus 1 by R2 in parallel connection. Here, this happens in series combination. It's inverse of what happens in case of resistance. So this is what we have done, combination in series. Let's take one simple example. How are these two capacitors? Are they connected in series? Which are the two capacitors? These are two capacitors. How are they connected? This is the wire which is joining to. Is this connection direct? Yes, this is a direct connection. It's a series connection. Okay, and find the charge on in capacitor and potential of the all plates, assuming potential of negative terminal of the battery to be 0. So which potential is I am assuming the potential of this battery to be 0. So you understand everything which is shown in green color. What is the potential of anything connected in green color? What is the potential of everything shown in green color? Is 0. If this is 0, since the battery has a potential of 10, negative plate being 0, the positive plate has potential of 10. Anything in blue color has potential of 10. But what about this part? There's third part also for which we don't know. This is 0, this is 10. We don't know what is the potential of the orange color. So how the two capacitors, equal capacitors of 10 microfarad each, are connected in series. Let's find out charge. And in terms of potential, I know X potential, I know Y potential. Only thing I need to find the Z potential. Let's see how do we do that. And we have to find the charge also. Let's pay attention what is simple method, and we'll repeat many times. So we pay attention every time we find easier. First, I find these two are connected in series. Replace these two capacitors with one single capacitor of equivalent capacitance. So this between they are connected between point X and Y. This are system of two capacitors connected between which 2 point X and Y. So I can replace these two capacitors with one single capacitor connected where? Again between same 2 point X and Y. How do we find equivalent capacitance? This is a formula. The same formula I can write equivalent capacitance is equal to C1 into C2 divided by C1 plus C2. So in this case, we easily find, we substitute 10 into 10 divided by 20. It is 5 microfarad. So what does it mean? I can replace this circuit and this circuit are equal. I can replace these two capacitors with one single capacitor, 5 microfarad. Once I have this circuit, I can easily calculate Q. This is a circuit which you know. What is the value of Q in the circuit? Q is equal to, we use the formula C is equal to Q by V, or Q is equal to CB. So what is the charge which will flow to the plates, or what is the charge which will move from negative side to the positive side? Our supplied battery is CB, and CB is equal to, we put those values C and B for 5 microfarad into 10, it comes equal to 50 microcoulomb. In series, we know if this supplies charge of 50 microcoulomb, all capacitors receive the same charge. So charge on this capacitor also will be 50 microcoulomb, and charge on this capacitor also is 50 microcoulomb by property of series connection. So this also 50-50. I have shown the charge only on the left plate, which is for plus 50. Right plate will be minus 50. This is charge distribution. Okay, so our 4 plates, we know what the charge is. Now, how do you find potential at point Z? Anybody can tell how do you find potential at point Z?
Q is equal to C1 into V1.
Yeah, basically we know potential. So this is this capacitor. We know the charge, we know the capacitance. I can find potential difference between the positive plate and the negative plate. Which formula? C is equal to Q by V. Potential left plate. What is, or if I apply the formula for left capacitor, potential of the positive plate minus the potential of the negative plate, which is Vx minus Vz, is equal to charge on the capacitor by its capacitance. Charge on the capacitor is 50, capacitor is 10 microfarad, so it comes equal to 5 volts. So if I substitute potential difference 5 volts, it means if this is 10, this is 5 volts. Vz is 5 volts. I could have same formula to this also come to the same result. So we know how to find charge distribution and potential of various points in the circuit. Simple enough. Let's do for all of you, repeat the same thing for this question. What are 3 things you need to find? Charge on the left capacitor, charge on the right capacitor, and potential of point Z. We know potential of X will be 10, potential of Y is 0. Find Vz and the charge on the 2 capacitors. Very similar way we had done before. So please solve that one.
Sir, we should find the potential at Z also here.
Yes. X and Y are already known. Exactly same thing what we done in the previous question, only just change the numbers. Those who have little difficulty, again I can look at that also. What he had done, this is what he had done. What we did, we are comfortable with one capacitor. We don't like many, so what he did, we replaced an equivalent capacitor using series formula. We identified these are connected in series. If they are connected in series, I have replaced the equivalent one. I have found out what the charge on this capacitor is. The charge on the equivalent capacitor is equal to charge on each capacitor. In series, this important point, charge on equivalent capacitor is equal to charge on any capacitor. So since the equivalent capacitor has charge of 50 microcoulomb, these two also will have charge of 50 microcoulomb. We found the charge, and then we applied the formula C is equal to Q by V to one of the capacitor to find the potential. Exactly same thing repeat here. As soon as you finish your question, please raise your hand. I think this is less than 2 minutes question. But you're doing for the first time, so as practice, you find you can be able to do much faster. When you're doing for the first time, perhaps it takes a little more to figure it out. Okay, so some of you have an answer. Okay, again, see some of those who are still not clear. Let me repeat step by step all the steps involved. Before I start the question, one thing I should know, one formula I know is what? I know the formula C is equal to Q by V for a capacitor. C is equal to Q by V. That's a formula I know. So if voltage is given, capacitance is given, I can find out charge or any of such things. So when I look at this thing, I find, okay, the voltage, I can't apply that formula because there are two of them. First thing I need to notice what kind of connection these two have. Okay, let me see, sir. Anybody who has not understood, please raise your hand. And I'll lower all the hands. See who are the people who are not understood. So those who are not understood, I'll explain the point which you have not understood. Hemant, have you understood?
Yes, sir.
No problem.
No, sir.
Ritika,
Yes, sir.
you understood?
Yes, sir. Yes, sir.
So I don't have to explain again step by step. Okay, anyway, let me repeat. If you most of you understood, step one is I start thinking. How do I start thinking? I know for capacitance, I know the formula C is equal to Q by V. Three quantities are related. I have to find the charge here. I need to look at this. I know the formula for one capacitor. There are two of them. So what I do first, I think of replacing two with one equivalent capacitor. What kind of connection is this? I check they are connected. They are connected by this connecting wire here. This is the direct connections. Hence, I conclude these two are connected in series, apply series formula. What I do, I replace them with an equivalent capacitance using series formula. Equivalent C is equal to C1, C2 divided by C1 plus C2. So 13 to 60 by 90. So the equivalent capacitance is equal to 20 microfarad. I replace with 20 microfarad. Now this circuit, I know the value of V. V is known and C is known. I can find Q. What is Q equal to? Q is equal to 100 microcoulomb. But I have found Q on equivalent capacitor. But in case of series connection, the charge on equivalent capacitor is same as charge on any of the capacitor. All are same. So if the charge here is 200 microcoulomb, charge on the two capacitor also will be 200 and 200. Two are also 200, 200. This plate will have plus 200. This will have minus 200. Again, this plate will have plus 200. This plate will have minus 200. So I found the charge. What I'm left with? I'm left with this potential here. Now on this capacitor, I have the charge as well as capacitance. I can find the potential or potential difference between two plates of the capacitor. So I apply that formula to find the potential at point Z. Vx minus Vz is nothing but potential of the positive plate minus the potential of the negative plate is equal to charge on capacitor divided by its capacitance. If I sum those values, it comes equal to 20 by 3 volts. Or Vz, what is Vz will be equal to? Vz will equal to Vx. Vx is 10 minus 20 by 3. So Vz will come equal to 10 by 3. I could have done a slightly different way also. If V1 and V2, what is V1? V1 is potential across first capacitor. V2 is potential across second capacitor. So V1 plus V2 is equal to 10. So 10 gets shared in form of V1 and V2. But which proportion does it get shared? It gets shared in form of inverse proportion of C1 and C2. So I can write V1 by Y2 is equal to C2 by C1 and V1 plus V2 is equal to V. Based on that, I can also calculate what is V1 equal to potential drop. It is not potential, so potential across the plates of capacitor V1. Since it is inverse, what comes in the numerator is not C1. What comes in the numerator is C2. V1 is equal to C2 divided by C1 plus C2 into V. That's another way we can calculate. That's a yes.
Yeah, so in that case, we won't need to find the equivalent capacitance, right?
Yes, we don't have to find equivalent capacitance. So suppose the question was only to find potential drop across 30 microfarad capacitor. Using this way, I don't have to calculate. I don't have to calculate equivalent one. I don't have to calculate charge. Straight away, I can distribute the potential in inverse proportion. I have to distribute between how many of them? Two of them. In which proportion? Inverse proportion of capacitance, which is very easy to do. I could have done that also. Now we come to other combination. Okay, yeah, this time I think we can do. How are these connected? This kind of connection is called parallel combination. Let's try and understand why it is called parallel combination. C1 and C2 are connected in parallel. So let's look at this. All the top half we look at. All top half are like one conductor. Is it not? All of them are at the same potential. Everything above here is if this point has this. See, all three are connected across terminals X and Y. X and Y are the terminals of battery. Three capacitors are connected like this. This is called parallel combination. Let's define what is parallel combination. What is top plate is having potential X. Bottom plates of all three have potential Y. So all capacitors are connected across identical potential points. Thus parallel connection. What is parallel connection? All are connected across identical potential points. Our potential drop across all the capacitors are equal. Then only they are treated as parallel capacitor, not because they look like parallel. So three capacitors C1 and C1, C2, C3 connected in parallel because A1, A3, A5 all at potential same as Vx, and lower plates A2, A4 and A6 all at the same potential, Y potential. They are connected across identical potential points. That's called parallel combination. So again, what we'll do here, again something similar, two things, charge and all. So there are 2 point connected points X and Y, and battery is connected. So battery will supply, so battery a potential which is connected with positive terminal X and negative terminal to Y. Battery supplies a charge Q. What will happen? Battery, it doesn't matter for battery, it supplies from here how much charge goes, how much Q charge goes from here. But when the charge Q reaches this junction X here, some part of Q charge will go to A1, some will go to A2, and some will go to A3, and some will go to A5. Here, what is happening? Previous case, charge was same, potential was getting distributed. What we notice here, the charge is getting distributed across three plates, potential remains the same. So, battery supplies charge plus Q, which gets distributed on three positive plates A1, A2, A3 as Q1, Q2, and Q3. So this charge Q goes here. We are tracking one side only. Same story will repeat on the other side. This is Q goes here. And as Q goes here, where has Q1 got? It has this Q1 here, this Q2 here, and this Q2 here. Since all three plates and negative plates all will receive same thing. If this is Q1, other one has to be minus Q1, minus Q2, minus Q3. Because net has to be 0 and charges on opposite faces equal and opposite. Then what is, since potential of each capacitor is same, Using C is equal to Q by V, what is Q1 equal to? Q1 equal to C1 into V. Potential across this capacitor also is V. This also V and this also V. I can calculate Q1, Q2 and Q3. Q1 is equal to C1 into V. Q2 is equal to C3 into V and Q3 is equal to C3 into V. This Q1 plus Q2 plus Q3, if there's an equivalent capacitance C, that capacitance also, equivalent capacitance C also draws a charge Q. Then what has to happen for this capacitance to be equal? This Q has to be, this charge Q drawn here also has to be same as charge drawn here by 3 capacitors. What are you going to do? Charge supplied by the battery must be equal to sum of charges on capacitors. We take all this capacitor C or this charge Q on equivalent capacitor CB is equal to sum of charge on 3 capacitors. And we get the formula of equivalent capacitance is nothing but sum of individual capacitors. C is equal to C1 plus C2, C3. In parallel connection, it is something similar to what we had in case of series connection for resistance. So like we summarize series connection, how did we summarize series connection? In series connection, I used 3 points. What are the 3 points I used? Series connection, the plates are connected directly to each other. Hence, the charge on the capacitors connected in series are same. And potential gets shared in inverse proportion of potential. Sorry, potential gets shared in inverse proportion of capacitors. What is same in case of parallel plates? What is same in case of parallel combination? Potentials are same.
So how can we say that?
How we say?
How can we say the potential is same?
I think I repeated 3 times. Try and tell now. What is how many conductors you see now? In this case, if you have to add all top half is connected together or not? See, if I look at this, see, will the potential of plate A1, will it be same as potential of plate A3 or not?
Yes, sir.
Why?
They are connected.
Connected together. So potential of A1 is equal to A3 is equal to A5, which is same as potential X. And lower potential plates also same potential. So it means potential across this, whatever potential difference this capacitor has, same potential difference this has, same potential difference this has. So I repeated also again to repeat, what is a parallel connection? In parallel connection, if 2 or more capacitors are connected in parallel, only if they are connected to identical potential points. So here also, C1, C2, C3, which are the potential points they are connected to? All are connected to one plate connected to X potential, other is connected to Y potential. All are connected to identical potential points, or potential difference is same across all the capacitors connected in parallel. Potential is common. What is shared here? In case of series, potential was shared, charge was common. Here, what is potential is common, charge is shared. Which proportion is the charge shared? Charge is equal to, we see here, charge is equal to C1 into V. V is same is charge is proportional to capacitance. Charge is shared in proportion of capacitance. So in parallel connection of capacitors, the potential of all are common and charge is shared out in proportion of capacitance. So these are the 2 key points in terms of parallel connection and series connection. Okay, let me ask some of you, series connection. Series connection, I hope all have followed. Akul, can you repeat series connection? Perhaps what are the key points related to series connection? I'll repeat again. What are the points related to? I'll repeat the point related to series connection. Capacitors are connected. Plates of the capacitor are connected directly without any branch. They form isolated system, hence charge on all capacitors connected in series are same. But they share the potential applied in inverse proportion of capacitors. Similar points if I make in case of parallel combination, I will say all capacitors are connected to identical potential points. Potential difference is same for all 3 capacitors. Second point, potential is common, but charge is shared. Which proportions, whatever charge the battery sends, it gets shared in which proportion? Charge is shared in proportion of capacitance. Q is directly proportional to C because of that formula itself. And what is the equivalent capacitance? C is equal to summation of C1 plus C2 plus C3, or I could have written as sum of Ci. So these are the key points which you need to remember. We have done this a couple of questions on series capacitors. Similar we will do on parallel as well. And these are fairly simple points. All of it should be comfortable. So can you, okay, whom did I ask? Okay. Akshay. Akshay?
So,
Can you tell me what are the key points related to parallel combination of capacitors?
C is equals to
What are points I mentioned related to parallel combination?